Welcome to Chapter 11, Geometry students. We are talking today about, in this whole chapter, about areas of polygons and circles. And today we're going to specifically look at angle measures in polygons. But before we get started in the lesson, I just wanted to show you this. I thought it was pretty cool. You've got the Giant's Causeway here in Ireland. You have these naturally occurring, more or less regular hexagons. Some of them look a little different in terms of where'd my pen go. I don't know. Where are you, pen? That's no good. Take my mouse a second. And so you see these like spires or basaltic columns, I guess is what we're calling them. Giant's Causeway. I'd love to visit there someday and check this out for myself. But pretty cool place. You might think of some other places where polygons, regular polygons, occur in nature. Hexagons, another place I can think of is a beehive, and pretty cool that the bees do that they, and the wasps, I guess, too. Do wasps have rectangular or have hexagons? I don't know. I think bees definitely do, but I think wasps do as well. I'd have to look at a wasp hive, I guess. But let's get into the lesson here and talk about what we're supposed to be talking about a little bit more here. I'm getting sidetracked. I'm interested in real life things. That's a good thing. Okay. But angle measures in polygons, that's what we're talking about here today. And I want to start with talking about the sums of angle measures in polygons. And rather than just giving you the formula, I don't think that's as helpful as what I'm about to do. So if I just give you the formula, you'll probably forget it or be like, where did that come from, and have a hard time remembering it. But if you write this down, which you're doing for me if you're one of my students, I think this is going to help you a lot in terms of remembering why the formula is what it is. If you can do that, that always helped me back when I was a student in high school, college, trying to actually know where things came from in math. If I could understand where the thing came from, then it was a lot easier to remember what it was in the first place. Okay, so a triangle, any old triangle, any old quadrilateral, it doesn't have to be any special kind. So I'm trying to draw non-regular shapes here. A pentagon just has 5 sides. All these are going to be convex, not concave. There's no parts that are caving in here. And a hexagon, just make sure it's got 6 sides there. Okay. And so a triangle, how many degrees in a triangle? We should know this from before. There's 180 degrees in a triangle. How many sides does it have? It's got 1, 2, 3 sides. As we move through this, you may start to notice a pretty cool pattern. Alright, before I draw in some extra things in here, let's just remind ourselves a quadrilateral, this is something we learned before, was 360 degrees, and that has 4 sides. So to me, I look at that, it went up by 1 side and this went up by 180. Do you think that pattern is going to continue? If you go up by another side, do you think you're going to add another 180? The fact is, it does continue. So it's 540 degrees. And then here, go up by another 180, it's 720 degrees. So you go up by 180 every time you add a side, but why is that? Why does that actually work? Why does that always work? Think of it like this. So go back, take out your different color at this point, and think of splitting a quadrilateral up into what am I making here? Diagonal right there, 2 triangles. You've got 180 and 180 right here. Pentagon you can split up into 3 triangles. Doesn't matter which vertex I would start with first. If I just make the diagonals there to the opposite vertex like that, and then I've got 3 triangles. Take a hexagon, pick any vertex, and connect it to all the non-adjacent vertices. You're going to make 4 triangles. So this is just 1 times 180. This one's just 2 times 180. This one's 3 times 180. And 4 times 180, that pattern continues. So you notice 4 triangles, 6 sides. 3 triangles, 5 sides. 2 triangles, 4 sides. And what's the formula there? What's the connection? What are you driving at here, Mr. Wagner? Yeah, every time if you take the number of sides and subtract 2 from it, that's how many triangles you can make. So you're going to take this number minus 2 and multiply it by 180, because each triangle will give you 180 degrees, and you have what the formula is in general for any n-sided polygon. Okay, so in general, let's write this down. This is the biggest thing, or at least one of the biggest things for this lesson. So in general, for any n-sided polygon. Or n-gon. It doesn't have to be regular. Regular meaning that all angles and sides are all the same. It doesn't have to be like that. Just for any n-sided polygon, the sum of the angle measures is always equal to n minus 2 times 180. You can always make that many triangles. We multiply by 180 because a triangle is 180 degrees. And so this is the big kahuna, one of the big kahunas for this lesson. Where am I going with that? I don't know. Where we go? That's better. And this is Theorem 11.1. So let's put that off to the side there. And there's a corollary to this theorem. Corollary, hopefully you remember, is something that follows directly from the theorem. So this is a corollary to Theorem 11.1. So it's actually another theorem, but it's like a one step after proving this theorem. We could say that this would have to be true as well. So also the measure of each interior angle in a regular n-gon. So notice the difference here. This was any n-sided polygon. Did not have to be regular, but if it's regular, all the angles have to be the same, meaning that this would have to be the formula to find a single angle in a regular n-gon. N minus 2 times 180, all divided by the number of sides, n. So this follows directly from this theorem here. So let's check out a couple of examples where we see these things put into practice. I'm going to draw a pentagon. I'm going to try to draw it as close as I can to scale, but it's not going to be perfectly to scale, and so I don't want to make the sides quite that big. Let's try that instead. There we go, that's fine right there. I want this one to be 105 degrees, so I'm going to open that up a little ways like that. This one I want to make 102 degrees. Okay, maybe something like that would work. 135 degrees. So 90, I want to go halfway between 90 and 180. Something like this. And then this one I'm going to make a little smaller than 90. I don't know how much. And that one I want to make a little bigger than 90. And let's give these things some labels here. This is going to be 114 degrees right there. 105 degrees here. 102 degrees here. 135. And we're calling this one X. And so what is X? That's what I want you to try to figure out here in this one. That's what we're going to tackle together here. Well, could we go back to this and say, oh, Mr. Wagner, you did this already for us. A pentagon has 540 degrees. Yes, but I don't want you to forget what the formula is. So you can always go back to this formula. Take your number of sides, minus 2, and multiply it by 180. Remember, we could split this into 3 triangles. That's why this works. So first of all, let's determine that the sum of the angle measures equals, in this case, 5 minus 2 times 180, which is 3 times 180, which is 540. This works no matter how many sides you have. If it was a 21-gon, you would take 21 minus 2 times 180. You can make 19 triangles out of a 21-gon. But for here, they should all add up to 540. So it's a pretty easy problem, I hope, from there. If they're going to add up to 540 and we've got 4 of the angles, we just need to take all these, add them together, subtract that from 540 to get what x is. So we have x is going to equal 540 minus those 4 that we know added together. And if you add these 4 numbers together, let's see what that would give us here. 540 minus, this would be 219, 319, 321, and 456. Yep, 456. Okay, and so 540 minus 456. Put that into a calculator, work that out in your head or longhand. Any one of those 3 ways should give you 84, and it would be, since x has the degree mark there, I'm going to leave off the degree there, but if you put the degree sign there, I wouldn't get too wrapped up about that either. So x equals 84, and if you plug that number back into the picture, it's 84 degrees right there. So if you add those 5 numbers up, you should get 540. That's a way to quickly check your answer and make sure you did it right. Number 2, or example 2. These ones are pretty quick, but example 2, now we're going to check out the corollary. I want to see us use this now, the corollary to theorem 11.1. So we're going to have a regular polygon. So each angle in a regular polygon has measure of 165 degrees. And it's regular, so that's pretty important. It's gotta know that to be able to figure this out. How many sides does the polygon have? That is the question. Okay, so we're going to use that corollary. And right here, I think this is valuable to write down here. So let's go back to example 1 and write, this was theorem 11.1, and now we're going to use the corollary to theorem 11.1 instead. So we're going to have n minus 2 times 180. That's the total of the angles, the total sum of the measures of the angles. Each one is the same, so we're going to divide that total sum by how many sides there are, by how many angles there are, and that should equal the value that's given to us, 165 degrees. Okay, so this was the corollary to theorem 11.1. So be thinking of this. Don't draw this off to the side. I just want you to think of this. Basically, this is what's going on here. We've got 165 degrees. I didn't make that big enough. So think of an angle like that, 165 degrees. That's going to be pretty wide open there. So you're hardly going to be able to tell that there's an angle. This is a regular one of these, so it's going to keep going like this and this and this. There's going to be a lot of sides to this one. I don't know how many sides exactly. Don't draw this again, but it's going to be, it seems like it's going to be a lot of sides. And the more and more sides you get, more and more it starts to look like a circle, actually, which is a pretty huge mathematical idea. That's how we kind of come to pi in terms of the number pi, not the stuff you eat, but pi. Mathematically delicious. And so I want you to take this. Let's take our different color and think of multiplying both sides by n. We want to get rid of the fraction if we can, and so that's really the easiest way to do this. This is definitely the easiest way to do this. Multiply both sides by n. And so you're left with n minus 2, still in parentheses, times 180, would equal 165 times n, or 165n. Think of distributing the 180, even though it's on the right side, it doesn't matter. You're still going to distribute the 180 to both parts. It's a minus sign. That's a little weird looking. There we go. And then we could subtract 165n and add 360, or we could just subtract 180n, have a negative number here, but then just divide by a negative number to get our final answer. So negative 360 is the same as negative 15n, or equals negative 15n. We can divide both sides by negative 15 to find out that this polygon would actually have 24 sides to it. So this is a 24-sided polygon. So this picture is actually kind of close. I just kind of trailed off here because I didn't know exactly how many sides it had, but these angles were pretty wide open, and so we're going to have quite a few sides with something like that. Let's move on now to the other big kahuna in this lesson. It's called the polygon. We've been dealing with interior angles. This is the polygon exterior angles theorem. And this is theorem 11.2. So the polygon exterior angles theorem. Think about exterior angles. That's something we should remember from previous courses. You don't have to draw this for me. I don't want you to draw this actually right now. This is just to quickly make a point. So let's say we had a hexagon. The exterior angle would be something like this. We're talking about the angle right here. That would be an exterior angle to that hexagon. And so what it says that the sum of measures, so the sum of the measures of the exterior angles in a convex polygon is always, pretty crazy that this always works out, but it's always the same exact number. It's always 360 degrees. So if I were to take this picture real quick and draw all the exterior angles, I don't know that they're all the same, so I'm not going to put arc marks on each one, but I'm saying all of these ones, if I were to add up all 6 of these exterior angles, what it's saying is that one plus that one plus that one and that one, that one, and that one should add to 360. It's always going to work like that, no matter if it's regular or not. If you had another weird one, maybe something like that, if you add all the exterior angles here, 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 and here, it's saying that those are all going to add up to 360 as well. No matter what polygon you draw, they're always going to add up to 360. And there's a corollary to this as well. So this is theorem 11.2. This is the corollary to theorem 11.2 down here. It's that the measure of each exterior angle in a regular n-gon, it's got n sides, a regular n-gon, it's got to be regular though, so imagine a regular n-gon. Now let's make an octagon. Just don't draw this again, but just to look at. If you were to take each one, you got each exterior angle here, boom, 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 these are all going to be the same, and since they are all supposed to add up to 360 and each one has to be the same, since it has 8 angles, you would just take 360 and divide it by 8 in this instance. In general though, you take 360 and divide it by n. So I should say is, there we go, is 360 divided by n. That's the big thing to remember there. So it's that many 360 degrees divided by n. If this was regular, it would be 360 divided by 5. If this was regular, 360 divided by 6. So let's check out a couple of final, pretty quick examples. I want you to draw a parallelogram, or something that looks like a parallelogram. And we'll have this one leaning to the left. And I want you to draw in the exterior angles here, 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 and here, like that. And so we're going to say that this one's 2y degrees up here, and so is this one. Those are the same, 2y degrees and 2y degrees. And this is y degrees, and this is y degrees here and here. And so what theorem are we going to use on this one? Well, it's not regular, and so it's not the corollary, it's the theorem itself that they add up to 360. But using the fact that they add up to 360, we could easily solve for y from there. We can say that 2y plus 2y plus y plus y. I'm just adding all of the exterior angles. That should equal 360 degrees. This is by theorem 11.2. So write that off to the side there. Add these together, you get 6y equals 360. Divide by 6, and you've got your answer that y would be 60 right there. So I think a pretty straightforward, pretty easy one. Just remember all the exterior angles, add to 360. And now, example 4, if it's regular, let's say we have a regular hexagon now. So I want you to draw your best regular hexagon. And to assure us that it's regular, or to denote that it is, I want you to draw in all the arcs being the same, and also put tick marks on all the sides. If you have that, then you know that it is regular. They have all the same sides and all the same angles. And then let's draw in one exterior angle here. Let's call this x degrees. We had to solve for x in this one. Now we'd use the corollary to theorem 11.2, and to say it's 360 divided by, in this case, there's 6 sides, so it's 360 divided by 6. This is the corollary to theorem 11.2. That's what we're using to figure out that that is 60 degrees right there. So x is 60. This is a 6-sided polygon or hexagon. It's a regular hexagon. Remember, it's got to be, if you're going to use that corollary, it's got to be a regular polygon. This is a regular hexagon. And that'll do it for this lesson. I'm all done. We're all done. You're all done taking notes. Go back and review as you need to. Please use those extra examples in the book for additional things to look at to help you as you tackle this assignment. Alright, hope you guys are doing well today, and I'll see you later.